I am thankful to Dr. Mustafa Misbah, working at Electrical and Computer Engineering Department in Sultan Qaboos University as Associate Professor, for providing the PowerPoint slides for these lectures. I have slightly modified the original slides. Again, thank you very much, Dr. Mustafa Misbah. Assalamu alaikum wa rahmatullahi wa barakatuhu. Alhamdulillahi Rabbil Alameen. Wassalatu wassalamu ala ashrafil anbiya wal mursaleen. Today's lecture will discuss the stability of the linear systems. Before going to discuss the stability of the linear system, just we will quickly review the representation of the linear dynamic system. We represent the linear dynamic systems by a differential equation, and order of the differential equation represents the order of the system itself. In this system, n is the integer and this is the order of the system. Here, if we are looking, C of t is the output of the system and we say this is the response of the system. R of t is the input to the system and we say it is the reference input to the system. Here m is also an integer. Just remember, order of the system is determined by the highest degree of the derivative of the output signal. So as C of t is the output and R of t is the reference input to the system, we normally use the terminology that C of t is a response of the system due to the reference signal R of t. Here n is an integer, m is also an integer, and for strictly proper system we say that n should be greater than m, and if this happens we say the system is strictly proper system. On the other hand, if n is equal to m, we say the system is proper, but it is not a strictly proper system. In nature, most of the systems are strictly proper systems. If n is less than m, we say it is an improper system. Such systems are very rare in the nature. In the software we can create such systems. Then if the initial conditions of this differential equation are 0 and we take the Laplace transform of the input and output, and then we manipulate do some operation on the result, so it is possible to write the transfer function of the system like this. So the differential equation represents the time domain properties of the system, while the transfer function represents the frequency domain properties of the system. Here in this equation, s is the Laplace variable, and here if you see, the degree of the system is determined by the highest integer n over here. This equation we may write is equal to n of s and d of s. So a transfer function is always consist of a numerator polynomial and denominator polynomial, though it is the ratio of the Laplace transform of the output and the Laplace transform of the reference input. But if we are looking to the transfer function, it depends upon the parameters of the system, and the transfer function of the system does not depend upon the input and output of the system. The stability of the system depends upon the denominator polynomial, and we say to this polynomial sometime as characteristics polynomial. Characteristic polynomial. And zeros of the d of s polynomial determine the stability of the system. This topic we will be discussing in detail. We also say to these zeros of the denominator polynomial are also called, zeros of the denominator polynomials are also called poles of the system. So the representation of the linear dynamic system we discussed in the previous slide can be given by this equation. Here, if the input to the system is 0, so we say the system is homogeneous system. But if there is an input like this, then we say, if we have an input like this, we say it is non-homogeneous differential equation. And while you are studying in your mathematics course the solution of the differential equation, it has two parts. First one is the natural response of the system, and natural response of the system depends upon the characteristics of the system, and it does not depend upon the input of the system. But there is another solution to what we say forced solution, and the forced solution depends upon the input to the system. And the response of the system has two parts, like natural response of the system and the forced response of the system. So here if we see, we have CFT is the forced response and CNT is the natural response of the system. So both of them together form CFT as the response of the system. CFT depends upon the input of the signal. This means forced response depends upon the input, and the natural response of the system depends upon the system properties and characteristics. And remember, the performance of the system has two things. One thing is the stability of the system, which depends upon this part, while the other thing is the performance, which depend together with this part and this part of the system. So now we will be discussing the stability of the linear time invariant system. What is a linear time invariant system? LTI, linear time invariant. When we say invariant, we means the characteristics of the systems are not changing with time. So an LTI system is stable whenever the natural response of the system become 0 as the time is approaching towards the infinity. The second thing, the system will be unstable whenever the natural response of the system will approaches to infinity whenever time approaches to the infinity. A marginally stable system is the system in which the value of C and T remain bounded. It will not approaches to infinity, but it will be equal to a real number in the steady state. So it will approaches to some value alpha. So here we say that this alpha is the absolute value of the C and T, where the absolute value of C and T will converge. This means alpha belongs to R plus. So the consequence of these statements comes like this, that whenever the system is stable, the total response of the system will approaches to the forced response of the system whenever the time is approaching to infinity. Can you think that why this will happen? My question is, why this situation will happen? Think about this, try to answer. You can stop the uh, video and do it by yourself, and after that you can see that what is my answer for this. So in the previous slide we discussed that C of t is equal to CFT, the forced response, plus the natural response of the system. So for the stable system, C and T will approaches to 0. So whenever this will become equal to 0, so automatically the response will be C of t is equal to CFT. There is a question that if C of t approaches to infinity, is it because of the natural response of the system or the forced response of the system? So can you answer this question? So stop here the video and do it yourself before seeing my solution. So here it is very important to know that the system forced response depends upon the reference input. And if the reference input is bounded, the forced response cannot be infinity. And in nature, whenever we give input to the system, they are bounded. So this means it cannot become infinity in the finite time, or whenever R of t is bounded, this means C of t will remain bounded. So the force response cannot go to infinity, but the natural response depends upon the system characteristics. So if the system is stable, the natural response will be approaching to 0, but if the system is unstable, the response of the system will be approaching to infinity. So whenever we see that C of t, this means the total response of the system is approaching to infinity, it is because of the characteristics of the system whenever the input to the system is bounded. So now on this slide, we will discuss the stability of an LTI system in terms of the input to the system, and this is fundamentally a detailed explanation of the question which was posed on the previous slide. Like if the system has a bounded input and its output is also bounded, we say that the system is stable. So here bounded input we say BI and bounded output we say BO. So bounded input, bounded output, stable system. What is the meaning of this? That if we excite a system with an bounded with a bounded input and the output of the system is also bounded, we say the system is stable. So what is the meaning of this? That the reference input is bounded and the system output is also bounded. The meaning is that R of t, absolute value of R of t is less than infinity, and absolute value of C of t is also less than infinity. In this case, the system will be bounded input, bounded output, stable. And we say the system will be unstable whenever the input to the system is bounded, but the output of the system approaches to infinity as the time approaches to infinity. So here we said that a system is unstable if there exists a signal R of t, and this R of t is bounded. When we say the signal is bounded, we can write the absolute value of that signal is less than infinity. Then C of t tends to infinity as t approaches to infinity. So these are the properties of the unstable system. But here if we see for the stable system, the absolute value of C of t will be a bounded output for a bounded input signal. So here we further discuss the stability of the linear time invariant system. So the pole locations of the system determines the stability of the linear time invariant system. And when I am saying the pole of the system, as we studied in the on the previous slides, that G of S, the system transfer function, is N of S upon D of S. Then the zeros of this polynomial, to this polynomial also we say characteristic polynomial. So the zeros of these polynomials are the poles of the system. So this means the zeros of this polynomial, which is the characteristic polynomials, are also the poles of the system. And the stability of the linear time invariant system, we can it depends upon the location of the poles of the system. So the first thing we say that if the transfer function, here it is written G of S, we can also write it is T of S, is stable if all the poles of the system are in the left half complex plane. When we say in the left half complex plane, here we means that S is the Laplace variable, and this Laplace variable is a complex variable. Here if I draw it like S plane, to this we say S plane, so it has two parts, the real part and the imaginary part, omega, and normally we will be saying that S is minus sigma plus or minus j omega. So if the poles of the system are in this area to the left side of the complex plane, we say the system is stable. And the reason I will explain in few minutes. Here we consider that this sigma, the real part, this sigma is positive. Now if this sigma is greater than 0, then minus sigma will be in the left half plane. So if this is the situation, the sigma is greater than 0, and we take the inverse Laplace transform of the system whenever the frequency part is 0, this means j omega. So our response of the inverse Laplace transform of the system will appear something like this. And here it is a e to the power minus sigma t, and sigma is positive. So if sigma is positive, as the time approaches to infinity, a e to the power minus sigma t will also approaches to 0. This means the natural response of the system will approaches to 0. This means c and t will tends to 0, and we know that whenever c and t approaches to 0, the system is stable. Similarly, if there is a frequency part or complex part with this means the system is suppose underdamped system as you studied in chapter number 4, then the inverse Laplace transform of the system will become something like this. And again, if sigma over here is positive, so it will approaches to 0. And again, this means the natural response of the system C and T will approach to 0 as the time will approach to infinity. This means the system is stable. So we continue with the stability of the system on this slide. So we check that when will be the system unstable. A control system transfer function Ts is unstable if at least one pole of the transfer function T of S, transfer function T of S is located in the right half of the complex plane. Again, just to repeat, when we say complex plane, this means it is S plane. And here, just if I sketch, so if this is S plane, here it is sigma j omega. So if we have one or more than one pole in this region, this means the system is unstable. And this pole can be real or a complex pole. In both cases, the system will be unstable. So here we see that if sigma is negative, so minus sigma, the total number over here will become a positive number. This means for sigma less than 0, the pole S will be on the right half S plane. And whenever we get a pole in this region, this means the system is unstable. If there are many poles, and most of them, even if they are in the left half S plane, but a single pole in the right hand is sufficient to say that the system is unstable. So for unstable system, there can be one or more than one pole in the right half S plane. So here if we see, like in this case, whenever the pole is real pole, this means omega is equal to 0. So the inverse Laplace transform will appear in this format, and definitely minus sigma is a positive number. So a e to the power a positive number into t, whenever t tends to infinity, this function will become infinity. So the output of the system will be approaching to infinity. This means the natural response of the system C and T will tends to infinity. Similarly, if the pole is complex, so the same thing will happen. We know the response for the complex system is like this. So again, minus sigma will be positive, and a e to the power a positive number over here, real number, and t will approaches to infinity. as t tends to infinity. So here again C and t will approach to infinity and the system will be unstable. So there is one more uh, type of unstable system. On the previous slide, we studied that if a pole is on the right half S-plane here, or if we have a pole here and here, this system is unstable system because there are poles in the right half S-plane. But there is another type of unstable system that on the same location, if we have more than one pole, we say that they are repeated pole on the same location at the imaginary axis. Even then the system will become unstable. And this pole can appear, these multiple pole can appear on a single location at the origin, or they can be in any other place at the imaginary axis, like here minus plus j omega and minus j omega. If there is one pole over here and one pole over here, they will not generate an instability in the system. But at the same location, if there are more than one poles, then the system will be unstable. So this is what we discuss in this section, that if there are repeated pole on the imaginary axis, if there are repeated poles on the imaginary axis, then the system response will approaches to infinity as the time approaches to infinity, and the natural response of the system will approach to infinity, and this means the system is unstable. So if we take the inverse Laplace transform of such systems, so inverse Laplace transform will be in this format, and we know that whenever this k is greater than 0 and t approaches to infinity, then atk also approaches to infinity. So c and t approaches to infinity. This means the system is unstable. So we have studied that there are two type of unstable system, in two type of uh, unstable linear time invariant systems. Number one, that if there is if if there is one or more than one pole in the right half S plane, this means the system will be unstable. And the second condition is that if there are repeated poles on the imaginary, if there are repeated pole on the imaginary axis. We have another kind of systems to what we say marginally stable systems. So a marginally stable system is a system in which there is single pole on the origin, or there are conjugate complex pole on the imaginary axis and they are not repeated, the system will be marginally stable. In this case, fundamentally what happens, the output of the system is bounded. Output of the system is bounded, but it does not converge to 0. Like suppose I have a pole here and another pole here, they are on the imaginary axis. So their uh, inverse Laplace transform of the system will be somehow in this format. So this is a bounded output for a bounded input. This means the system is stable. Again, if I have a single pole over here and we excite this system by an impulse, the output of the system will be just a unit step function u of t. So u of t is bounded. This means the system is stable because the system gives us a bounded output for the bounded input. To such system we say that they are marginally stable system. So on this slide, we present the summary of the discussion till now. Uh, the system is stable whenever all of its poles are in the left half S plane. So there is no pole in the right half complex plane, or there is no pole on the imaginary axis. To such system we say that it is a stable system. Unstable system, at least one pole in the right half complex plane, and there can be some poles in the left half S plane and some poles in the right half S plane, but single one pole in the right half complex plane can determine that the system is unstable. Another thing, if there are multiple poles at the same location on the imaginary axis, the system will be unstable even if there is no pole on the right half S plane, and there can be some poles in the left half S plane. A system is marginally stable if there is no pole in the right half S plane. There can be some poles in the left half S plane, but there can be non-repeated poles on the imaginary axis. Non-repeated poles on the imaginary axis. On this slide, we will discuss one example related to the stability of the system. So we will discuss about the open loop stability and the closed loop stability of the system. So here this is the open loop system. Now if we look to the open loop system, there is one pole at -2, the other pole is at -1, and another pole at 0. So this means S is at the imaginary axis, which is at the origin. Therefore the open loop system 3 upon S into S plus 1 into S plus 2 is a marginally stable system. Now, as we studied the feedback loop system, it is easy to write down the closed loop transfer function of this system as g of s is the closed loop transfer function is equal to 3 upon s into s plus 1 into s plus 2 plus 3, and this will be equal to 3 upon s cube plus 3s square plus 2s plus 3. And now if we find the zeros of the denominator polynomial over here, zeros of this polynomial, so you will find them. These are the, so one pole we are getting here, another pole is here, like this is one pole, another pole is here, and the third pole is here. All of the three poles are in the left half S plane. This means the system is stable, and this system has complex poles, so the output of the step response of the system will have some oscillations. Here whenever we are writing that R of S is 1 over S, this means the input to the system in time domain is u of t. So The response of this system will be a bounded output because the closed loop system is stable, and the output of the system will be somehow like this. So initially we are looking that the in the transient stage there are some oscillations. So this is the natural response. But what will happen? This natural response will converge to 0, and the forced response like u of t, which was 1. So at the end the output of the system is going to converge to the forced response of the system. This means in the steady state the output of the system will be C of t will be equal to CFT. So on this slide we will discuss another example. So in this example, again the open loop system is stable. The only difference, in the previous example the gain was 3 and now the gain is 7. In this case the closed loop transfer function, we can write it very easily like this: g of s is equal to 7 upon s cube plus 3s square plus 2s plus 7. Now if we find out poles of the system, which are the zeros of the denominator polynomial, so you will see that they are here. So we see the complex poles are in the right half S-plane. This means the step response of the system will be oscillatory and diverging. Here, like if I see this is u of t is the unit step input, and the output of the system is the step response of the system. We can see the step response of the system will be looking like this one. So initially it start from 0, and the transient will never converge to 0. The transient is always increasing. So the system is unstable. And why? Though the open loop is marginally stable, but the feedback loop made it unstable system. So in many systems, if we increase the gain of the system can become unstable. Thank you very much.